All right, today we're putting on our detective hats because we're about to crack one of the biggest mysteries in all of science, the atom. We're going to follow the clues piece by piece left behind by some of the most brilliant minds in history to figure out what the universe is actually made of.
You know, it's a wild question, but the answer is pretty simple. Atoms. Everything, everything, is made of these ridiculously tiny building blocks. But for most of human history, what was inside them was a total secret. Our story, our investigation, begins with the very first clue that started to unravel it all.
So let's head back to the late 1800s. Back then, scientists thought atoms were the end of the line, just tiny, solid, indivisible little balls. But one scientist was about to stumble upon a clue that would change everything.
That scientist was J.J. Thomson. He's doing these experiments with electricity and gases, and he finds something that shouldn't exist. He realizes that atoms aren't solid little spheres at all. No, they have even smaller pieces whizzing around inside them. He had just discovered the very first subatomic particle, the electron.
So how do you do it? Well, he used this cool piece of gear called a cathode ray tube. He zapped a gas with electricity, and it created this glowing beam. Here's the clever part. He used magnets and saw that he could bend the beam. That proved it was made of stuff, of tiny particles with a negative charge. And since these particles came out of the atoms in the gas, they had to be part of the atom itself, a total game changer.
So now Thomson has to come up with a picture of what this new atom looks like. He imagines it as this ball of positive pudding, with his negatively charged electrons scattered all through it, kind of like raisins in a muffin or plums in a pudding. It was a fantastic first attempt, but it had one really big problem. It didn't explain where all the atoms' weight, its mass, was. The mystery deepened.
And that next clue, well, it arrived as a complete plot twist. Nobody saw this coming. This is where our detective story gets really good.
Okay, so enter Ernest Rutherford, who's actually one of Thomson's old students. He cooks up this experiment to prove the plum pudding model was right. The plan was simple. He'd shoot these tiny positive bullets, called alpha particles, at a super thin sheet of gold foil. If the atom was really like a soft pudding, these little bullets should just zip right through.
But that is not what happened. And you can just feel the shock in Rutherford's own words. Most of the particles did go straight through, just like he thought. But every once in a while, one of them would bounce almost straight back. That was supposed to be impossible. It just didn't make any sense with the plum pudding idea.
Let's break down what he was seeing. The fact that most particles flew straight through told him the atom must be mostly empty space. The few that got knocked off course a little bit must have been pushed away by something positive. And those incredibly rare ones that came flying back, they must have hit something tiny, incredibly dense, and positive, head-on. In that moment, Rutherford had discovered the atomic nucleus. So this discovery leads to a whole new model of the atom. Now it looks like a mini solar system, with a tiny positive sun, the nucleus, at the center, and the electrons orbiting around it like planets. But this created a brand new puzzle. See, according to the physics they knew at the time, an orbiting electron should be losing energy constantly, and it should spiral right into the nucleus, causing the whole atom to collapse in a split second. So why doesn't it?
The next piece of our puzzle comes from a physicist who looked at Rutherford's chaotic, unstable atom and decided to give it some rules. He brought order to the chaos. His name was Niels Bohr, and he knew that classical physics just couldn't explain Rutherford's model. So he did something incredibly bold. He decided to mix the old physics with some brand new and, frankly, very weird ideas from quantum theory.
Bohr's big idea was this. He said electrons aren't allowed to orbit just anywhere they want. They're stuck on specific paths, like trains on a track, called energy levels or shells. And as long as an electron stays in its lane, it doesn't lose any energy. It can just go around and around forever. The only way it moves is by jumping to another track, either by absorbing a specific amount of energy to jump up or releasing it to jump down. It was a simple, elegant solution that finally explained why atoms are stable.
So, now that we have a model that actually works, we can finally get a clear picture of the key players inside the atom. Let's do a quick roll call of the cast of characters in our story.
Okay, so we've got three main particles. Right in the center, crammed into that tiny nucleus, you've got the protons, which have a positive charge, and the neutrons, which have no charge at all. These two are the heavyweights. They make up almost all of the atom's mass. Then you have the electron, with its negative charge, just buzzing around the nucleus in those energy shells. It's incredibly lightweight, almost massless compared to the other two. Now, how do we keep all these different atoms straight? Well, we use a kind of shorthand, a special notation that tells us everything we need to know. Let's use carbon-12 as our example here. What do these two little numbers actually mean?
That top number, the 12, is called the mass number. It's super simple. It's just the total number of protons and neutrons you have in the nucleus, all added together. So for this carbon atom, it's 12. Easy enough.
Now the bottom number, the 6, this one is the most important number of all. It's the atomic number, and it's basically the atom's social security number. It tells you exactly how many protons are in the nucleus. And here's the key. Every single atom in the universe with 6 protons is a carbon atom, period. That number defines what element it is.
So what about those electrons zipping around? Well, they're the ones that determine how an atom actually behaves and interacts with other atoms. We call this its valency. It really all comes down to the electrons in that outermost shell. Those are the ones that do all the work, forming bonds with other atoms, always trying to get to that perfectly stable, full outer shell.
Okay, so we've cracked the code. We know what an atom looks like and what's inside. But so what? Why does this actually matter in the real world? Let's take a look at how we actually use this knowledge.
One of the coolest things about this atomic structure is that it allows for something called isotopes. So check this out. Both of these are chlorine atoms. They both have 17 protons. That's what makes them chlorine. But look closer. One has 18 neutrons and the other has 20. So they're the same element, they just have different weights. These different versions of an element are called isotopes.
And this is where it gets really amazing, because isotopes are incredibly useful. We use an isotope of cobalt to fight cancer. We use others to find tiny leaks in massive underground pipelines. The famous carbon-14 lets us figure out how old ancient artifacts are. It's like a scientific time machine. And of course, an isotope of uranium is the fuel that powers nuclear reactors. Understanding the atom's core has given us some seriously powerful tools.
So when you step back and look at the timeline, it's just incredible. In just a few short decades, our picture of the atom went from a simple plum pudding to a complex little solar system. Each detective built on the last clue until James Chadwick finally discovered the neutron in 1932, officially completing our set of subatomic particles.
Our detective story has taken us all the way from a fuzzy idea to a miniature planetary system. But in science, the story is never really over. Cracking the atom opened up the whole bizarre world of quantum mechanics. It just makes you wonder, what other secrets, what deeper mysteries are still locked away, waiting for us, inside the heart of matter?